Hello, welcome to the NMR Spectroscopy course. This is the lecture number 4. In this lecture, we will study the rules for predicting nuclear spin quantum number and some of the practical example. I am not going to discuss much of the theory with you because you can study the theory from the Google, but practical examples are more important, and many of them you can't find on the Google because they are much difficult and nobody will tell you exactly. So let's go to the spin quantum number. Today our topic is a spin quantum number, and spin quantum number maybe have the value of 0, 1 over 2, 1, 3 over 2, 2. So it is represented by the I. So these are the values, so on. So spin quantum number more than 7 over 2 is a very rare case. So you know that carbon 12 has 6 protons and 6 neutrons. The number of protons and number of neutrons are even. So like let's discuss in some simple way like this, as we do in the math, basic math. 6 proton, 1 2 3 4 5 6, 6 neutron. So 6 protons, 2 protons are paired up, like one have this spin and other have this spin. So plus half minus half mean these are cancelling each other. So 2 2 2, this. So all the spins have been cancelled. So there is no any unpaired proton or neutron or nucleon. Nucleon is the collective term used for the proton and the neutron. So how many nucleon in the carbon 12? So there are 12 nucleons. So let's take an other example in which we will use the odd number of the neutron, like odd number of neutrons and protons, like nitrogen 14. Nitrogen 14 has 7 protons and 7 neutrons. These 7 protons, in which 6 of the protons are paired up, and there is 1 proton which is not paired up. And in the nitrogen 14 there are 7 neutrons, 6 are paired up and 1 is unpaired. 1 is unpaired proton, 1 is unpaired neutron, and their spin is 1/2. So spin for the, this is neutron, spin for this is also 1/2. 1/2 plus 1/2 is equal to 1. So spin for this will be 1. If the spin is equal to 0, then we can't study those nuclei in the NMR spectroscopy. So there will be no NMR spectrum for those nuclei which have the spin state 0. So our spin should not be 0 if we want to study the NMR spectra of fuel. We can't detect them in the NMR. So for the complex systems, like if we have more protons or neutrons, these are some of the simple cases. But in the complex form, we can't we can predict, but it is very difficult to predict the how many protons are paired up and how many neutrons are paired up, and how many are unpaired neutrons, and how many are unpaired protons are present. So these are most difficult. There are many difficult examples for that. I am not going to discuss that. So there are some rules in the NMR spectroscopy. They have made these rules to predict that this should be the spin 0, this should be the spin 1 over 2, 1 half, 3, 5 half, 3 half, this that. So let's go on the next. So these are the rules, such as number of protons are even and number of neutrons are even. If the number of protons and number of neutrons are even, as we have taken the example of carbon 12, in the number of protons and neutrons were even proton and neutron were even. So in this case, nuclear spin will be 0. So when the nuclear spin will be 0, we can't detect it in the NMR. So the same case is with the oxygen 16. So it has the even number of protons, even number of neutrons, like 8 proton, 8 neutron, and carbon 12 has 6 proton and 6 neutron. So we can't detect these in the NMR. So let's take another case for the odd. For those who have odd number of protons and odd number of neutrons, their spin should be 1 or 2 or 3 or so on. So we have studied an example of nitrogen 14. It has 7 protons and 7 neutrons. So odd number of protons and odd number of the neutrons. So its spin should be 1 or 2 or 3, and we have already calculated it. Its spin is 1. So if the number of protons are even and number of neutrons are odd, or vice versa, like number of protons are odd and number of neutrons are even, then the nuclear spin will be 1 half, 3 half, or 5 half. Like take an example of carbon 13, because it is important, and F90. So carbon 13 has 6 proton and 7 neutrons, 6 proton and 7 neutron. So in this case, we have even number of protons but odd number of the neutrons. So even number of protons and odd number of neutrons will lead to, so it should have a spin 1 half, 3 half, 5 half. As this is a very famous nuclei, and we know that its spin is 1 half. Fluorine 19 has the same case. Its spin is also 1 half. So these are the some examples. You can take more example from the internet, and you can see that these rules are generally applied on I think on all the nuclei in the periodic table. So these are the examples for the today. We will study next about the spin quantum number, and we will calculate the spin states, how many spin states are there from the spin quantum number. Thank you for watching the video. If you like the video, subscribe the channel.